Hello everyone, a very good evening to all. Myself, Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So, again, I welcome you all for this ninth interaction session on the course Atomic and Molecular Physics with course code NOC 26PH18 being float by NPTEL in this January 2026 session. So, today we will be briefly discussing the concept that was covered in week 9 lectures, and then we will solve a few sample problems based on those concepts. So let's first discuss briefly about the concept that was covered in this week's lecture. So atomic spectra section was completed in the previous week or last week 8. So this week lecture was mainly about spectra of molecules. So molecular spectra. So week 9. So week 9 was about molecular spectral molecular spectroscopy. So in case of atomic spectroscopy, there are only electronic spectra because in an atom there is only electron and nucleus is present, and depending upon the level in which electron resides in, the energy can be changed depending upon the energy of the excited state or energy of the state in which the electron is. So we talked about structure of spectral lines. Like first we started with hydrogen spectra, then there are different theory which was explained uh, because some theory initially it had some drawbacks like that. Then we developed more models and more theories, and then there was fine structure of spectral line as a result of interaction between spin angular momentum and orbital angular momentum. Then, if the nuclear spin is also taken into account, then there is hyperfine structure of spectral lines. Then, when the atom is present in a magnetic field or in electric field, then there will be G-man or Stark effect, which will again lead to splitting of the spectral lines. Because we know due to vector atom model, the concept, an electron revolving in an orbital also act as a magnetic dipole. So, since it is a magnetic dipole, it will be having magnetic dipole moment. So, when an atom is placed in a magnetic, due to its intrinsic magnetic dipole moment, it will experience some force, and due to which the energy of the system will change, and depending on that, there will be spectral line splitting. But now we'll discuss about the molecules. Now, in case of molecules, what happens since there are more than one atom, like diatomic or different type, like there will be homonuclear molecule, heteronuclear molecule also. So, due to the relative motion, whether they are rotating or they are vibrating, then there will be different types of spectra. So, electronic spectra, rotational spectra, and vibrational spectra. So, there are three types of spectra that we will study in this molecular spectroscopy. One is electronic spectra, then rotational spectra, and then vibrational spectra. There are also pure rotational spectra, rotational vibration spectra that we will consider. Now, depending upon the energy levels, depending upon the order of energy, we can also correlate different spectra. Like if you talk about the energy order, in case of electronic spectra, it is in terms of EV, like a few EV, 0 to 10 EV. Like we discussed in hydrogen atom, the ground state energy is 13.56 EV. So the energy levels are, the spectra are of the order of electronic volts. So they lie in the region of visible and ultraviolet. Similarly, for rotational spectra, the energy is of the order of 10 to the power minus 3 electron volts. Since energy is very less, they correspond to microwave part of the electromagnetic spectrum. And then for vibrational spectra, the energy is of the order of 0.1 electron volt, and it corresponds to infrared region of the electromagnetic spectrum. So The molecules which undergo rotational vibrational motion, they can also be called as microactive or infraactive molecules like that. And again, now another spectra is called as pure rotational spectra. Pure rotational spectra or rotational vibrational spectra. So how we can so why it is named like that? Why it is pure rotational vibration? So what happens? Like, let's consider different labels. Suppose this is electronic label A, and this is electronic label B. Again, corresponding to each electronic label, there will be a number of vibrational label. So this is suppose V equals to 0, B equals to 1, B equals to 2. There can be also other labels, but let's for the timing we will consider only 3 labels. Similarly, for B, it will be B equals to 0, B equals to 1, B equals to 2. And corresponding to each vibrational label, there will be rotational labels. Like corresponding to V1, there will be a number of labels which will again named as J equal to 0, 1, 2, 3. So these are rotational labels because um, again for V equal to 1, there will be 0, sorry, 0, 1, 2, 3 like that. Similarly, in case of B also, there will be rotational labels. So now, if the transition occurs between the rotational labels of corresponding to a single vibration label, so now this transition it corresponds to B equal to 0 only. So it will be called as pure rotational spectra. But if the transition occurs from one rotational label of one vibration label to another rotational label of another vibration label, then it is called as rotational vibrational spectra. So this is pure rotational, and this is rotational vibrational. So that's why this is named like that. So now also there are different molecules like homonuclear molecule or heteronuclear molecule. So in case of homonuclear molecule, what happens? So for homonuclear molecule, the examples are hydrogen, oxygen, nitrogen, like that. So they have two atoms. They are similar. Then in case of heteronuclear molecule, it consists of different atoms like carbon monoxide, hydrogen chloride, sodium chloride, zinc sulfide, etc. Now these molecules, since they corresponds to so they consist of different atoms, so they will be having electronic label, the electronic energy plus rotational plus vibrational label. So due to the dipole moment, like the rotational energy comes due to their because when the molecule is having permanent dipole moment, so they will tend to rotate about some axis, then rotational spectra will occur. Similarly, vibration spectra. So then in general, homonuclear molecules that don't show rotational and vibrational spectra. Our heteronuclear molecules, they show rotational and vibrational. They undergo rotational and vibrational motion. That's why they show rotational and vibrational spectra. Let me add a few slides. So in this week, it mainly it was discussed about rotational spectra. So if you talk about rotational motion, the concept of reduced mass comes into picture, where mu is called as m1 m2 divided by m1 plus m2. And then there was a different type of rotational spectra, like one was rigid rotator and another was non rigid rotator. So in case of rigid rotator, what happens? The energy level is given in terms of h square by 2I j into j plus 1, where j is rotational quantum number. It can be 0, 1, 2 like that. But in case of spectroscopy, they are mainly represented in terms of wave number. So wave number means Ej will be energy divided by Hc. In that case, if you represent it, it will be h by 8 pi square Ic j into j plus 1, or you can write it as b j into j plus 1 in centimeter inverse, where b is called as rotational constant. Rotational constant h divided by 8 pi square Ic, where I is nothing but the moment of inertia, which is written as mu r square, and the concept of mu comes into picture when we are considering the motion of a rotational motion of a molecule. Similarly for non-rigid rotator, what happens? For non-rigid rotator, the wave number of the levels is given in terms of b j into j plus 1 minus d j square into j plus 1 whole square. So now in case of there will be transitions corresponding to rigid rotator and non-rigid rotator. For example, in case of rigid rotator, if you see, for rigid rotator, so j will be 0, then it will be 2b. Sorry, j will be 0. It will be 2b into 0. It will be 0. For j equal to 1, it will be 2b. For j equals to 2, it will be 6b. For j equals to 3, it will be 10b. But in case of non-rigid rotator, it will be different. For j equal to 0, it will be 2b into 0 minus, there will be this d term. Then for j equal to 1, it will be 2b minus 1 2 square. So 2b minus 4d. So the energy levels are again different. So the spectra will also be different. So we will discuss about this concept in more details when we solve the problem. So now let's start with solving the problems of today's interaction session. So the question number 1, it says two masses m1 and m2, where m1 is greater than m2, are separated by a distance r. The reduced mass of this system is mu. Then option A, mu will be greater than m1. Option B, mu will be less than m1 but greater than m2. Option C, mu will be less than m2. Or option D, mu is equal to m1 plus m2 divided by 2. So now again it is represented by, so again this is related to the reduced mass, concept of reduced mass. So the reduced mass is given by mu. The reduced mass is given by mu, and this is a system of two masses. A system of two masses m1 and m2. So now we need to find out whether mu will be less than m1 greater than m2, and whether it will be greater than m1 or less than m2. So I'll give you a few minutes and then we'll discuss what will be the correct option. So if we discuss, so the concept of reduced mass is basically used to simplify a two-body problem. Like here we have given in the question it is given there are two masses M1 and M2 where M1 is greater than M2. Now also there are different situations where we need to consider two different masses, like the case we considered in case of hydrogen atom. What happens? An electron, a single electron, it is revolving around the nucleus, so we can nucleus, and in hydrogen, in case of hydrogen, the nucleus is only a single proton is there inside the nucleus, no neutrons. So that we can consider as a two-body problem. Like the electron, it is revolving around a proton. So there also we used the concept of reduced mass, so that instead of solving different equation of motion for different masses, like for proton and for electron, we converted the whole system into a single mass, which is reduced mass mu. And what was the formula for reduced mass? It was mu is equals to m1 m2 divided by m1 plus m2. So the two body problem, it is converted into a single effective mass. So that will be a single body problem, and we can solve for a single equation of motion. Now this basically represents the effective inertia of the system if we are considering the relative motion. So these are different applications for reduced mass. Now let's consider our question. So in question it is given m1 is greater than m2. So now let's solve whether it will be greater than m2 or less than m2. So now we know mu is equals to m1 m2 divided by m1 plus m2. So if we divide m1 on numerator and denominator, then it will be m2 divided by 1 plus m2 by m1. So when in the question it is given m1 is greater than m2, so m1 is greater than m2, that implies m2 by m1 is less than 1, but 1 plus m2 by m1 it is greater than 1. So mu is m2 divided by some number which is greater than 1. That means mu, it is less than m2. Again, if you divide with m1 also, so when mu it is, we divide m1, sorry, first we divided it with m1, so this m1 plus m2, so divided by m2 it will be m1, 1 plus m1 by m2. So in that case also mu is less than m1. So mu is less than m1 and mu is less than m2. So mu is less than both m1 and m2. So if you see the options, mu will be less than m2 is the correct option, because here it is mu is less than m1 but mu is greater than m2. It will not be correct. Again it will be not correct. And this is m1 plus m2 divided by 2. Again this is not correct. So the correct option will be option C, mu is less than m2. So now we move to question number 2. Question number 2 says, arrange the following EM waves in increasing order of frequency. Option A, infrared, microwave, X-ray, gamma ray. Option B, microwave, infrared, X-ray, gamma ray. Option C, gamma ray, microwave, X-ray, infrared. Or option D, X-ray, gamma ray, microwave, infrared. So all these, they corresponds to the electromagnetic spectrum. Electromagnetic spectrum. So we need to find out in order of increasing frequency what will be the correct order of these regions: infrared, microwave, X-ray and gamma ray. So I'll give you a few minutes and then we will discuss what will be the correct answer. So now if we see the electromagnetic spectrum, now this is the electromagnetic spectrum. So as you can see, the frequency is increasing in this way, and the wavelength it is increasing in this way. So here in our question it is increasing order of frequency, infrared, microwave, X-ray and gamma ray. So increasing order of frequency will be microwave, infrared, X-ray and gamma ray. So microwave 1, infrared 2, X-ray 3, gamma ray 4. So it will be, first it will be microwave, then infrared, then X-ray, then gamma ray. And if you consider about the frequency, so microwave it is corresponding to gigahertz 10 to the power minus, so microwave it is 10 to the power of the order of 10 to the power 9 hertz. Infrared it is of the order of 10 to the power 12 to 10 to the power 13 hertz. X-ray corresponds to gigahertz 10 to the power 18, sorry not gigahertz, 10 to the power 18 hertz. And gamma ray it is the most energetic, it is corresponding to 10 to the power 20. Similarly, if we talk about wave numbers, there will be decreasing order of wave numbers. So microwave it is 10 to the power minus 2 meter. Infrared it will be even lesser, 10 to the power minus 5 meter. X-ray will be 10 to the power minus 10 meter, that is Armstrong or nanometer, 10 to the power minus 10 meter. And then gamma ray 10 to the power minus 12 picometer, 10 to the power minus 12 meter. So the correct option is microwave, infrared, X-ray, gamma ray. Correct option is option B. I hope this is clear to you. Now we move to question number 3. So question number 3 says, which of the following molecules is or are microwave active, and consider they are rigid models, because in case of non-rigid the things will be different. So in case of rigid model, in case of non-rigid what happens, the bond also vibrates, or then we need to consider the other things, but here we need to consider only the rigid model, because the bond length does not change. And we need to find out which of these molecules is or are microwave active. Microwave active means they undergo rotational motion. So I'll give you a few minutes and then we will discuss which of them will be microwave active. So now, so the microwave active molecules are those molecules which can absorb or emit microwave radiation because they undergo rotational transition, and the molecule with permanent dipole moment, they are called as microwave active because the microwaves they interact with the electric dipole. So there, if there is no dipole moment, there will be no interaction and there will be no absorption of the microwave. So the microwave active molecules are those molecules are uh, which have permanent dipole moment. So now let's consider the molecules. So what we can write, the molecules having permanent dipole moment are called microwave active. So now you can clearly see the molecule H2, it consists of two hydrogen atoms, so it won't be microwave active. And there are other molecules, one is CO2 and the HCl and OCS. So in case of CO2, what happens? CO2 is a linear molecule. CO2, it is a linear molecule. So this is C, this is O, and here this is O. So the bond length is same in both the side. So it has zero dipole moment. It has zero dipole moment. Now let's consider OCS. So OCS is a linear molecule. So OCS, it is a linear molecule where one side is sulfur and another side is oxygen. But here the bond length are different because the moment in CO side is different from moment in CH side. So here it is, so the bond length it is 115.75 picometer, and here it is 156.01 picometer. So since the bond lengths are different on both the sides, so and O has more electronegative than carbon, so the bond length is lesser in this side. So due to this type of structure, it has permanent dipole moment. So it has permanent dipole moment. Now let's consider the fourth molecule, which is HCl. Again, HCl, it is a heteronuclear molecule because so in splitted into Cl plus H plus and Cl minus. So the molecule has permanent dipole moment. So the correct answer is HCl and OCS. So these two molecules are microwave active. So the correct option is option B, HCl and OCS. I hope this is clear to everyone. Now we move to question number 4. Question number 4 says, let the moment of inertia of a molecule is in three directions are Ix, Iy and Iz, then asymmetric torques are those for which option A, Ix is equals to Iy is equals to Iz, option B, Ix equals to Iy greater than Iz, option C, Ix equals to Iy less than Iz, or option D, Ix not equal to Iy not equal to Iz. So these are the four options and we need to find out if the moment of inertia, suppose this is a molecule and it has three directions x, y, z. So the moment of inertia along x is Ix, this is Iz and this is IY, then asymmetric tops, who have then in which case it will be called as an asymmetric top. So that we need to find out. So I'll give you a few minutes and then we'll discuss. In which case it will be called as asymmetric top. So asymmetric tops are those molecules for which the principal moment of inertia they are different in all different directions, like Ix is not equal to Iy is not equal to Iz. So Ix it is not equals to Iy, it is not equals to Iz. Correct option is option D. Now to question number 5. Question number 5 says the J equals to 1 0 to 1 transition in HCl occurs at 20.68 centimeter inverse. Considering the molecule as a rigid rotator, calculate the wavelength of the transition occurring from J equals to 14 to 15. So options are option A 28.05 micrometer, option B 30.27 micrometer, option C 32.23 micrometer, option D 35.07 micrometer. So again we need to consider the concept of rigid rotator. So for transition 0 to 1, the wave number is given, it is 20.68 centimeter inverse. So now we need to find out the transition, the wavelength corresponding to the transition. So you can see it is wave number is given and we need to find out the wavelength, and the transition is J equals to 14 to 15. So I'll give you a few minutes and then we will discuss what will be the correct answer. So now see we before solving the sample problems, we briefly discussed the concept of rigid rotator, and in that case, we saw when the transition occurs from j to j plus 1, when the transition occurs from j to j plus 1, then the wave number corresponding to the transition, it is given by 2b j plus 1. Now, given that transition from 0 to 1, so here j to j plus 1, so here j is 0. So in that case, the wave number will be 2b into 0 plus 1, that is 2b, and it is given as 20.68 centimeter inverse. 20.68 centimeter inverse. That implies what is b? B is 10.34 centimeter inverse. That is 20.68 divided by 2. Now let's consider the transition from j equal to 14 to j equal to 15. Now when the transition occurs from j equal to 14 to j equal to 15, so j to j plus 1, so j is 14. So in that case, what will be the wave number? It will be 2b into j plus 1, that implies 2b into 14 plus 1, 30b. So 30b means 30 into 10.34, which is 310.2 centimeter inverse. So now corresponding, so now wavelength is 1 by wave number, so it will be 1 by 310.2 centimeter. So it is 0.003223 centimeter, and the options are given in micrometer. So we need to multiply 10 to the power 4 here. So it will be 32.23 micrometer. So the correct answer is 32.23 micrometer, that is option C. I hope this is clear to everyone. Now we move to question number 6. Question number 6 says the transition from j equal to 3 to j equal to 4 in HCl molecule, it is associated with the radiation of 83.03 centimeter inverse. Considering the rigid rotator model, calculate the moment of inertia of the HCl molecule. Options are option A 1.54 into 10 to the power minus 46 kg meter square, 3.05 into 10 to the power minus 45 kg meter square, 4.32 into 10 to the power minus 45 kg meter square, or option D 2.69 into 10 to the power minus 47 kg meter square. So I'll give you a few minutes and then we will discuss what will be the correct answer. So if we solve it, again it is similar to the previous question. So again, when the transition occurs from j equals to 3 to j equals to 4, the wave number corresponding transition will be 2b j plus 1, 2b into 4, 8b, and it is equals to 83.03 centimeter inverse. Now we know what is B. So 8B is 83.03 centimeter inverse. Then B will be how much? 83.03 divided by 8, which is 10.37 centimeter inverse. Now what is B? We know B is given by H divided by 8 pi square IC, and this is 10.37 centimeter inverse. Now the question is in meter square, so we need to convert it. So it will be 10,1037.875 meter inverse. That implies I will be H by 8 pi square B C. So H is 6.626 into 10 to the power minus 34 into 10 to the power minus 8 up C. So it will be 8 into 3.142 square into 1037.875 into 3 kg into meter square. Now what will be I then? It will be 6.626 divided by 8 into pi square into 1037.875 into 3 into 10 to the power minus 42 kg meter square, 0.0000269 into 10 to the power minus 42 kg meter square. That implies 2.69 into 10 to the power minus 47 kg meter square. The correct answer is 2.69 into 10 to the power minus 47 kg meter square. Now I move to question number 7. So question number 7 says, what is the number of degeneracies of the rotational energy level considering the rigid rotator model for rotational quantum number J? So what will be the degeneracy of the rotational energy level if we consider the rigid rotator model for rotational quantum number J? Options are option A, J into J plus 1, option B, J square, option C, 2j square, or option D 2j plus 1. So we know for a given j, mj can take values from minus j to plus j in integer steps with 0 included. So for j, mj will be mj will be having value from minus j to plus j, including 0. So it will be 2j plus 1 values. So the degeneracy is 2j plus 1. Like L had values 2L plus 1, like that. So now I move to question number 8. So question number 8 says the rotational energy difference between two consecutive labels for rigid two consecutive labels like J plus 1 and J for rigid diatomic molecules in terms of wave number, that is nu by C, varies with rotational quantum number J as. So these are the options. Option A, so these are the four figures, figure 1, figure 2, figure 3 and figure 4, and we need to find out the correct option, whether it will be figure 1 or figure 2 or figure 3 or figure 4. So this is an interesting question, so that we will solve how we can relate in terms of the graphs presented here. So I'll give you a few minutes and then we will discuss what will be the correct answer. Now let's solve it. So if we talk about the transition that is occurring from j occurring between two consecutive labels j and j plus 1. So we know the web number, it is given by for j label. What is the web number? It is given as ej divided by hc, which is h by 8 pi square ic j into j plus 1, and it is called as b j into j plus 1. Now for j plus 1, what will be the web number? B j plus 1 j plus 1 plus 1. It will be b j plus 1 into j plus 2. Now if the transition occurs from j plus 1 to j plus 2, when transition is occurring from j to j plus 1, so in that case it will be new per j plus 1 minus new j. So it is b j plus 1 into j plus 2 minus b j into j plus 1. b j plus 1 we can take common, j plus 2 minus j. So it will be 2b j into j plus 1. Sorry. So j will get cancelled out. So it will be 2b into j plus 1. So we can say that the web number, it is directly proportional to j plus 1. So let me add another slide. So when j equals to 0, it will be 2b. When j equals to 1, it will be 4b. J equals to 2, it will be 6b, like that. Now if we consider the equation, the relation, it is like y is equals to mx plus c, where c equals to y at x equal to 0, and it is 2b. So what will be the relation? It will be the equation of straight line passing through the point 2b on y axis. So this is j and this is new bar. So this will be the answer, and the correct option will be option A, that is figure 1. I hope this is clear. Now we move to question number 9. So question number 9 says, let the moment of inertia of a molecule in three directions are ix, iy and iz. Then spherical tops are those for which ix is greater than equal to iy is greater than equal to iz. Option B, ix equal to iy greater than iz. Option C, ix equal to iy less than iz. Or option D, ix equals to iy, ix not equals to iy not equals to iz. So the previous question was related to asymmetric top. Now it is spherical top. So what will be the correct option? We will discuss it after some times. we know for a molecule to be called as symmetrical top, its moment of inertia should be symmetric in all three directions. So the molecule having moment of inertia equal in all three directions are known as spherical vectors. So Ix equals to Iy equals to Iz. Option A is the correct option. Now I move to question number 10. Is the last question of protein interaction session, and the question says the rotational kinetic energy of pure rotational spectra for carbon monoxide molecule for a given level is given by Ej is equals to 7.6 into 10 to the power minus 23 joule. If the moment of inertia of carbon monoxide is 1.45 into 10 to the power minus 46 kg meter square, then the angular velocity of the carbon monoxide in radian per second is. So here E is given. It is 7.6 into 10 to the power minus 23 joule, and the moment of inertia it is given 1.45 into 10 to the power minus 46 kg meter square. Then what will be the angular velocity in radian per second? The options are option A 1.35 in 10 to the power 13 radian per second, option B 1.05 into 10 to the power 11 radian per second, option C 1.024 into 10 to the power 12 radian per second, or option D 1.59 into 10 to the power 10 radian per second. So here we know the rotational kinetic energy is given, and it is pure rotational spectra of carbon monoxide molecule. So from rotational kinetic energy, you need to find out the angular velocity. So I'll give you a few minutes for you to solve this question, and then we will discuss what will be the correct answer. So we know the rotational kinetic energy is given as Ej is half I omega square. So omega will be 2e by I root over, so 2 into 7.6 into 10 to the power minus 23 divided by I is given 1.45 into 10 to the power minus 46 root over, it is 0.2 into 7.6 divided by 1.45 into 10 to the power 24 root over. It is 1.0238 into 10 to the power 12 radian per second, or we can say omega is 1.024 into 10 to the power 12 radian per second. So the correct answer is option C, 1.024 into 10 to the power 12 radian per second. So with this we come to the end of today's interaction session. I hope the questions that I have solved covering the topics of rotational etc. of a molecule, that will definitely help you in solving your course assignments as well as in your preparations for the exam. So I will hope that in the upcoming sessions I will be able to solve your doubts as well as solve the problems related to the week 10 of the course content. With this, we will end the interaction session now. Thank you all.